Okay, we are going to get started with our seminar this week. So our speaker with us today is Jonah Dimnik, and Jonah completed his undergraduate here, specifically a Bachelor of Science at the University of Calgary in the Mechanical Engineering program, and had a specialization in biomedical engineering. And during his undergrad, he did a research project on continuum damage models of fatigue and failure in whole bones. Currently, he's a master's student here in kinesiology at the University of Calgary, working under the supervision of Dr. Brent Edwards. And his project largely focuses on the topic of this presentation today, so finite element model prediction of bone strain and microdamage accumulation in bones. Some interesting facts about Jonah are that he trains service dogs, he loves to hike, and he also coaches youth football. So we're looking forward to your talk, and thanks.
Awesome. Okay, well, thank you very much for the introduction. So as mentioned, today I'll be talking a little bit about some CT-based finite element analysis and how we've been using this over the past year or so to try to predict bone strain and microdamage accumulation. So today I'll be presenting some preliminary data and results. This work is ongoing, so there's plenty more to do as I continue on in my graduate degree here. So I'd like to begin by going over the stress fracture process and stress fractures in general. So what they are and why we even care about them. So up at the top there, we kind of have a very simplified model of this stress fracture process. It's of course much more complicated than this. And right now we're just focusing on the mechanical factors of stress fracture, but there's much more to this on the biology side, which we leave out for right now in the work that I'm presenting today. And so a stress fracture is a biomechanical event resulting from mechanical fatigue. And so you can see with every stride that this runner takes, he's generating this ground reaction force, and that's not the only thing at play. Of course, we have all the muscle forces acting on the tibia as well. And so all of these mechanical loads are examples of this repetitive mechanical loading that can lead to the accumulation of microdamage. And if that microdamage isn't repaired by the bone remodeling process, it can coalesce, eventually initiating a crack. This crack can propagate and go further and further until we reach a point of fatigue failure. And this is where we see stress fractures, or in the most severe case, complete bone fracture. So if we take a look at the X-ray image here at the bottom right, this was taken from a professional soccer player after a season, some pretty rigorous soccer training. And you can see pointed out by those little arrows, that's a tiny little stress fracture. And to the untrained eye, you might look at this and think, well, it's so minuscule. You know, what's the big issue, right? Allow some time to rest, heal, and eventually return to sport. But to kind of emphasize the severity of some of these fractures, this is another X-ray image taken from that exact same soccer player after he had to undergo a fix using a full-length rod and 3 screws. And so these injuries are by no means insignificant, and in fact, up to 15% of female runners will experience a stress fracture at some point in their life. Now, the real kicker for me is that these injuries can be entirely prevented. But the key to prevention is prediction. And so before I get too ahead of myself on this prediction front, I need to talk a little bit more about this concept of microdamage accumulation. So microdamage accumulation, or this fatigue damage, it physically manifests in the formation of these microscale cracks and voids. And you can see some examples of that here at the bottom of your screen. We typically use something called the damage fraction to assess how damaged bone might actually be. So this is a value that ranges from 0%, where we have a completely intact, undamaged bone, all the way up to 100%. And this isn't really reasonable to conceptualize, because at that point, we're really just dealing with entirely cracks and voids and no real bone material. But what we do see is that at around 30% damage, we're either right on that cusp of failure or having observed the bone failed already. And so you can imagine that this damage would probably impact or negatively affect the material properties of bone. So here on the left, we just have what we could imagine being a cross section of bone. It's nice and white. There's no cracks, no voids, so it's completely undamaged. And what we do is we take the area of this cross section of undamaged bone, and we get this total area of undamaged bone. That's our A naught. And of course, associated with this cross section, we would also have the material properties of that particular bone. And so we're really talking about this initial elastic modulus in that cross section. Okay, so now you can imagine that if we go ahead and load this cross section of bone and we continue to load that, we'll start to accumulate this microdamage. So these cracks and voids begin to form, and we could go ahead and count up all these cracks and voids, and we take their total area, and we're finally left with this total damaged area. And when we take the ratio of this total damaged area to that total initial area, we get exactly that. That's the damage fraction that we've been talking about in the previous slides here. And so again, we look at this cross section of bone, and we have some bone material and then some material that's really just these cracks and voids. And so now there's less actual bone material there resisting this compressive loading. And so again, you can kind of imagine how this leads to detrimental impacts on the material properties. And in fact, that's exactly what happens. So our damaged elastic modulus comes as some reduction due to this damage factor of our initial elastic modulus. And so as we keep that in mind, if we're looking at this repetitive loading during the fatigue process, we might say on this first cycle of loading, we don't have any damage, so our damage fraction is 0, and that would mean that our damaged elastic modulus is really just the same as that initial modulus because no damage has been incurred. But if we continue to load this bone, maybe we get to a point where we have 25% damage, and so that damage acts on the elastic modulus, and we really only have 75% of that elastic modulus remaining. And we could do this more and more, and maybe we get to a point where we have 50% damage, so our damage fraction is 0.5. And so, of course, we're left with only 50% of that elastic modulus. And so having a little bit of background of this concept of damage, I'll now go into this stress fracture prediction concept and how we might actually go about doing this. So if we were working with traditional engineering materials that have this very homogeneous material properties, we would use something called the stress life approach. And so what we do is we take a bunch of those material samples and we fatigue load them through a range of different stress magnitudes, and we cycle those loadings until we finally observe failure, at which point we have that fatigue life. And so we could go ahead, again, doing this across a bunch of different material samples, different ranges of stress, and we can develop an SN curve like we see here on the left. And so if I wanted to get an idea of how long a particular component or material would last before we can expect failure, well, I would look at what stress magnitude that material is experiencing, and then I could go ahead and consult the SN curve for that material. And then we can read directly off what the fatigue life or the expected number of cycles it could endure before failure. And so again, this works quite well with these traditional engineering materials. But when we're looking at something like bone, and even in the most idealized case where we have these small machine samples of bone, we see a ton of scatter in this data. And so the scatter can even span these orders of magnitude. And so of course, there are some challenges with this SN approach, particularly when we're working with bone at the whole bone level, and we're no longer at that little small machine sample level. And so when we're at that whole bone level, bone really has this very unique geometry and heterogeneous material properties that span that entire volume and geometry. We also, of course, have to account for those nonlinear effects of fatigue damage that we've been discussing. And so this really results in a big redistribution of stress and strain throughout every single loading cycle. So again, we get this damage that affects the material properties. And so with each loading cycle, material properties degrade, and then the stress and strain redistribute across that whole volume of bone. And so what we've done is we've implemented this CT-based finite element analysis to address these two problems. And of course, we have to have a way to quantify this damage. So when I've been talking about damage this whole time and using this damage fraction where we can actually count up those cracks and voids and take that damaged area, well, this is kind of a histological approach, and we can't exactly do that, particularly if we're trying to predict stress fracture. We couldn't do that to human bone if we're trying to make these predictions. And so we developed a continuum damage mechanics model to actually compute that damage, and we use a strain-based damage model, which we'll go into depth on a little bit later here. And so with that, it brings me to this more refined approach that we've proposed and we've been implementing over the past year or so. And so what we've done is we start by taking a CT image of our bone of interest, and from that CT image, we get this 3D model, and we can create a 3D mesh over that entire model. And to that mesh, we go ahead and assign our heterogeneous material properties and determine these loading and boundary conditions. And so this whole part is really just developing that FE model. But then we have a second part here where we kind of take these FE models into Abacus, and we use a combination of Python scripting and an FE simulation software like Abacus to first actually apply the load to that model. We then go ahead and check if it's failed. So we're looking to see if the bone's broken at this point. And if it hasn't, we continue on to calculate that damage as a function of strain, use that damage to reduce the elastic modulus, and then go back and update every single element with their new material properties. And we sort of iterate this process over and over again until we find that we have met that failure criterion, at which point we can calculate and output the fatigue life. And so we can get predictions for this damage accumulation and also the fatigue life of that particular bone. So we separate these into two different studies, so each one of these components. And on the left, this is our first study where we're really looking just at that FE model development. So this is everything going from the CT scan all the way to determining these loading and boundary conditions. And we're finally left with the FE models that we'll be using in our second study. And the goal of our second study is to actually develop this program, so implement it programmatically to be able to predict the damage and eventually the fatigue failure of bone. Now, in both of these cases, we use a rabbit animal model. We do this for a number of reasons. The biggest one is it's really practical for the work that we're doing. So of course we have to fatigue load these bones. And so the rabbit model is a very suitable animal model for this work. But also, as we continue to expand this work and improve it, I talked about earlier how we're talking about this stress fracture process and only looking at the mechanics of it, but there's a huge biological component associated with the bone remodeling process. So in the future, we really have to use a rabbit animal model. It's the smallest animal that shows this human-like intracortical remodeling to develop and improve this model to also account for that entire biological process. And so that's kind of the reason behind using this rabbit animal model. And with that, I'll talk a little bit more specifically about study one. So again, as a reminder, this is everything to develop that FE model going from the CT images and then finally to those boundary conditions and loading conditions. And the big challenge with this is determining and actually assigning these very accurate material properties. And in order to assign these material properties, what we've done, and again, as you'll see over and over again, we're starting with this CT image of our bones of interest. And so we're working with this rabbit animal model. So these are some rabbit hind limb bones. We have some tibia bones and some femur bones. And then from this CT image, we can go ahead and segment out our bone of interest that we actually want to perform our analysis on. We also include a calibration phantom in our CT image. So I know many people in this room are probably familiar with CT phantoms or have used them in their own work before. But just as a little reminder to go into detail, what these phantoms have are these hydroxyapatite inserts, and each one of those inserts have a known density. So when we include this in our CT scan, we can go ahead and look at these grayscale values or the Hounsfield units from our CT scan, and we can convert those into units of these hydroxyapatite equivalent bone density values. So we get a function, something like equation 1 here. So it's really just some linear function that takes these Hounsfield units and converts them into units of hydroxyapatite equivalent bone density. And of course, we still need to get from these density values into our real material properties, which is our elastic modulus. And so what's been proposed in the literature and what we use in our work here is something like a power law relationship shown in equation 2 there. So we have this relationship that takes our hydroxyapatite density values and converts those into our elastic modulus. And finally, using this equation 2, we can go ahead and look at every element in that model and apply the appropriate material properties. And so we end up getting a bone that looks something like this. So we have this very heterogeneous material property distribution where we're looking at these kind of red elements. These are these elements that probably have the highest density or the highest elastic modulus. And as we move into these greens, yellows, and blues, those are areas where we have lower density or lower elastic modulus. And now just as a note, so you might see these kind of caps at the end of these bones. This is really just for our experimental setup. So this is a bone potting material. And what we do is we kind of cement the proximal and distal ends of each one of these bones. And the reason behind that is so that we can just fix it in our loading apparatus to do the experimental testing that we need to. So that's the reason for those little caps on the end. But looking back at this equation too, so we see this nice power law relationship, but we still don't know these values of A and B. So what are those values going to be to actually convert from these density values into our elastic modulus? And in fact, there have been a wide array of density modulus relationships that have been proposed in the literature. And even when we group these relationships by things like the anatomical location, the specimen geometry, the loading conditions, there still remains a ton of scatter. And so we don't really know which relationship needs to be used. And the study of our first objective is to determine that optimal density modulus relationship for the rabbit hind limb. So in order to determine that optimal relationship, what we've done is we had to find whichever relationship could be used in order to minimize the difference between the finite element predicted bone strains and those same strains that we measure experimentally. So once again, to do this, we start same process as always with this CT image of the bone that we need, and then we can go ahead, create the mesh, the 3D model, and apply those loading and boundary conditions. Now at this point, I'll just briefly touch on finite element analysis for anyone in the room who's not very familiar with this process, and this is a super, super high level explanation. But essentially, we're taking this big model and we mesh it into these thousands of little elements. And so effectively, we're taking a very large, complicated problem and breaking it down into these many smaller components. So each one of these elements become kind of its own mechanical problem. And we can kind of see how if you solve for a mechanical solution of your choosing in one element, the output of that element becomes the input to the next, and then the output of that, the input of the next, and so on and so forth. And so we really get solutions to these problems across the entire geometry, the entire volume of the bone. Now, of course, when we're looking at this equation 1, so our density modulus relationship, well, each one of these elements will have a particular grayscale value, and so a particular Hounsfield unit associated to it that we get from that CT scan. And so if it has a unique density value, then all of them, no matter what we use for our parameters A and B, will get a very unique and different elastic modulus as well. And so again, this is kind of to emphasize how heterogeneous these material properties are when we work with these finite element models. So what we did was we took an initial guess at these A and B values, so just a model that we've seen to perform relatively well in the literature. And we went ahead and applied that material to the entire model, and we run that simulation and get our initial or our first strain map output. And so it looks something like that there on the left, but we take this exact same bone, and of course we mechanically load it experimentally as well. So it looks something like this here. And we measure the strain on the surface of the bone at various locations of interest. And we do this experimentally, and we have those saved. And we could go ahead and compare those strains measured at the surface of the bone to the exact corresponding locations in the finite element model. And so we go ahead and make that comparison. And then we went back and we changed those parameters A and B. We rerun the model, we get a different strain distribution. And then we do the exact same thing where we compare the strains at those exact corresponding locations. And so we do this process iteratively over and over again. And so we're adjusting these parameters A and B until we find the mean squared error between the FE predicted bone strains and the experimentally measured bone strains is eventually minimized. So this process as a whole is called optimization. And here we've employed the Nelder-Mead method to optimization. And in terms of computation time, this takes somewhere between 12 and 24 hours to run. This is highly dependent on how many bones that you're optimizing on. So this is for somewhere between 4 to 12 bones. Will take around 12 to 24 hours. And so once we obtained those optimal parameters for A and B, we have this final density modulus relationship. This is what the FE predictions look like in comparison to these experimental measurements of bone strain. So here on the left, we have our FE predicted bone strains plotted against our experimentally measured bone strains. It's bounded by our 95% confidence interval, and that black dotted line in the middle is the line of unity. So if we have an ideal relationship, then our y will equal x, and our points will fall directly on that line of unity. And our linear regression revealed that this FE model was able to explain up to 97% of the variation in these experimentally measured bone strains. Now, looking over here on the right, we have our Bland-Altman plot, and we can see relatively good agreement across the board. We do have this average bias of about 87 microstrain. And so for the work that we're doing here, and as we go into study 2, we're actually looking to predict that damage accumulation and fatigue failure. We're really only concerned with the tibia because that's what that model is based on. But we did this optimization for the entire rabbit hind limb. So we did this in 3 separate groups. We just show the tibia here, but we did this for the femur as well. And we did this in a group where we combined both the tibia and femur bones. And we saw relatively good agreement and strong correlation across the board. So in our femur, we were able to explain 73% of the variation. And in this combined group, we were able to explain up to 82% of the variation. And so now we can return back to our second study. And again, this is the study to be able to predict that damage accumulation and fatigue failure of bone. So our objective in this study was to programmatically implement this approach that we've been talking about there on the left to, again, go ahead, predict that damage accumulation and fatigue failure. So as a bit of a reminder of this process, if we kind of zoom in on an element level, so if we're looking really close at these elements in the model, we're just assuming that there's squares there. Each one of these elements will have that initial elastic modulus that we've applied using that density modulus relationship. And so as we continue to load this model, you see that those elastic moduli degrade further and further until we eventually reach a point where they're effectively completely damaged and no longer providing any structural support to the model. So at this level, when we're looking at the elements, we've really observed failure in those elements. They no longer have any stiffness or elastic modulus associated to them. But when we go to this whole model, when we're looking at the whole bone, we can't really look only at the elements. We have to look at the behavior of the model entirely. And so in that case, we're really just looking at the total stiffness of the model. But these elements that are degrading underneath is what's actually reducing that stiffness. And so here on the right is the actual programmatic implementation of this cyclic process that we've talked about on the left. And so this is a Python script that we implemented, and it's doing the exact same thing as what we've gone through. And just to quickly step through it, so it starts by generating a unique input file that comes from the finite element modeling process that we did in study 1, generates that input file, and then we iteratively run these FE simulations until we find that some failure criterion is met, at which point we can go ahead and calculate and output our fatigue life. But of course, with every one of those iterations, we also have to calculate that damage and update the elastic modulus for each one of these elements. So for this entire program to work, we still had to address 2 key components of this model, which are how exactly do we go about checking for failure or determining that failure criterion, and how do we calculate our damage as a function of strain. And so to start in determining our failure criterion, we began by fatigue loading 6 rabbit tibia bones till failure. And here we're showing their stiffness degradation plots across their entire fatigue life. And so if we go back and maybe look at a more characteristic stiffness degradation plot, it should look something like this. And so kind of recalling back to the very start of our presentation where I've been talking about this 30% damage concept where we expect bone to fail at that point, what we should see is that damage starting to degrade our stiffness. And so we should also see that at around 30% stiffness loss, kind of on that cusp of failure as well. And so what we did is we went ahead and took the stiffness at failure. So this is our KNF. And we take the ratio of that to our initial stiffness, our K naught. And this allowed us to determine the stiffness loss-based failure criterion. And we show this here in equation 1. We found that on average for all of these bones, they tended to fail at about 25% stiffness loss. And so again, thinking back to that 30%, we're kind of right in that range, which is really nice to see. We also did a sensitivity analysis on this criterion, which revealed that when we varied this stiffness loss failure criterion between plus or minus 10%, the fatigue life predictions weren't very sensitive to that change anyways. And so again, we felt confident using this going forward. So once again, this is that programmatic implementation, and we've just talked about how we go ahead and determine failure. And so as a reminder, we're really looking in the finite element model, and with every iteration, we're assessing the stiffness of the bone. And so at the point where we see that 25% of that stiffness has been lost, that's the point where we meet the failure criterion, and we can go ahead and calculate and output our fatigue life. So we've talked about that, but in each one of those iterations, we still need to calculate the damage and update the elastic modulus. And so what we opted to do was to adapt a damage model proposed by Cotton and colleagues, as shown here in equation 1. So this is a strain-based damage model. We use a von Mises equivalent strain, and this really gives us just a nice scalar value to be able to calculate our damage for each one of these elements. We also have this delta n parameter. So this is called a time step parameter. And really what we're doing is we're linearly scaling the damage value across a number of different cycles so that we don't have to run a single simulation for every single loading cycle. And as you'll see, that becomes very computationally intensive. So in this case, we still have that exact same problem that we saw earlier with our material model. So we don't know what these constants A and B should be. And what we did, of course, is run another one of our Nelder-Mead downhill simplex optimizations. And in this case, we're optimizing the parameters A and B such that the mean squared error between the FE predicted fatigue life and experimentally measured fatigue life is minimized. And this process, of course, becomes much more computationally intensive. So when we think back to this material model optimization, again, we were looking at somewhere between 12 and 24 hours, depending on how many bones we were optimizing on. But when we run this damage model optimization, we're now looking at something between 1 and 2 months before we find that optimized model. So what's this reason for such a dramatic increase? Well, again, when we think back to this material model, every time we ran an optimization iteration, we're only submitting one FE simulation. Now, when we do this damage model optimization, every time we have to run one iteration, we submit this entire Python script. And so this script can run hundreds of simulations. Again, that's just for one iteration. So at the end of the day, we're kind of submitting multiples of hundreds of Abacus simulations. And of course, this adds up to a ton of computation time. We're kind of waiting around 1 to 2 months. Once we do that, we finally get this damage model or those optimized parameters for A and B. And we wanted to see how this damage model and this process as a whole performs on a completely different set of bones that it hasn't been optimized for. And so again, we went back and repeated this same process. We take a different sample of bones, we fatigue load them till failure, and we take the FE predictions and we compare those to the experimental measurements. And this is what it looked like. So on the left, we have, again, that experimental fatigue life measurement plotted against our predicted fatigue life, the same 95% confidence interval, and that black dotted line as our line of unity. A linear regression revealed that we could explain up to 71% of the variation in experimental fatigue life. If we look over at our Bland-Altman plot here on the right, it reveals that we have an average bias of about 0.64 log cycles. And we kind of have a tendency to overpredict fatigue life in this low cycle regime. And so this data probably doesn't look the prettiest, but what I will say is when we're looking at fatigue life predictions, specifically at the whole bone level, it's actually extremely challenging to be able to explain up to 71% of the variation in that experimental fatigue life. But something that I think is more interesting and what you certainly cannot do with an SN or stress life type of approach is actually look at the fatigue behavior. So predicting how this bone will behave throughout the entire fatigue life. So here on the left, again, we show that characteristic stiffness degradation plot, and we have our predicted fatigue behavior in blue. And on the right, we have the total displacement. And again, that predicted behavior in blue. This isn't the best performing sample. It's certainly not the worst performing sample, but it's somewhat of a representative sample. And we can see that this model does a relatively good job at kind of following that expected fatigue behavior. And finally, here we show the damage accumulation across the entire fatigue life. So starting up from our first loading cycle there on the top left and all the way through to the final loading cycle at its fatigue life, we can see that with every increase, we're starting to accumulate more and more damage. And what we did is whenever we saw an element reach a particular critical damage threshold, we went ahead and removed that from the simulation. So this actually has no impact on the mechanical behavior of the model because essentially we're really degrading that elastic modulus of those elements. And so they get to a point where they're effectively providing no mechanical support. And so it's just air there. So we can remove it from the model, and that allows us to observe these sort of fracture patterns and locations in the bone. And what's super interesting and surprising to me is when we go ahead and look back at these experimental samples, well, we're really seeing these fracture patterns in the exact same locations. So here we have one up at the proximal tibia and a second one in the fibula. So the same that we see in our FE models that we've observed experimentally. And I think this is super encouraging and kind of gives us a bit of an additional layer of confidence that we're really modeling what we're intending to model. And so I hope in the future, we can actually kind of expand this to intentionally predict these fracture patterns and locations and give an idea of what we could expect there. And so just to summarize some of the stuff that I've talked about today. So again, our ultimate goal was really to be able to predict damage accumulation and fatigue failure in whole bone. And I personally hope that in the future, we can improve this and expand it to predict stress fracture itself. But at the very least, we should be able to provide some insights into the etiology of stress fracture. And again, what we did in doing this was develop this CT-based finite element analysis method for whole bone fatigue. And we sort of addressed these three different objectives in doing so. So of course, we had that Nelder-Mead optimization to determine our power law density modulus relationship. And then we wrote that Python script to implement this process as a whole and predict fatigue life. And finally, we of course had to run another optimization to get this ideal damage model to make that entire script work. And so once again, this work is very ongoing. So there's plenty more to investigate and improve. First and foremost, we certainly need to increase the sample size when we develop both of these models. That makes it much more robust and hopefully more accurate in its predictions. And we'll also look at investigating different failure criteria and damage models and compare how those perform. And so with that, I'd just like to thank the entire Edwards group, especially Dr. Brent Edwards, and also Kurt Wild, who has been helping me out a lot on this project and that first study for our density modulus relationship. Thank you all for your time, and I'll take any questions if you have them.
Awesome. Thanks, Jonah. Any questions to start us off? Yeah, Venus.
So your model is based on the accumulation of fatigue until we reach the failure stage. But I'm wondering, like, if I am running or not, but if it's like in real life, you're not considering that that is happening to the tissue during, like, between the cycles.
Mm-hmm.
So you have any comments about that?
You're exactly right. And so that's kind of why I mentioned earlier on, that's the exact reason why we're working in this rabbit model, because it does show that human-like intracortical remodeling. And so right now, we're really only modeling the mechanical behavior. But in the future, that's exactly the plan. So we hope to actually consider those remodeling effects. And the process of remodeling is quite complicated and not super well studied. And so that's kind of where this work is going. And we'll actually begin to incorporate the remodeling so that if we do eventually use this to predict stress fracture in the future, of course, we have to account for that remodeling process between each one of those cycles. So you're totally right. That's exactly where this is going.
Along the same line, if you're not considering the remodeling, then the coefficients that you calculate from the optimization, would you expect that to be changed for someone in the future trying to use that model? They have to correct for that.
It's a really good question. When we're talking just about the damage model itself, the damage, as far as I know, I may not be correct on this, but it shouldn't really be at least heavily impacted by the remodeling process. Now, what the remodeling will do is repair that damage. So I do think that the damage will be incurred in much the same way, and this model would probably work relatively well in doing that, but we then have to account for how that damage gets repaired. So it would kind of be a feedback loop. We still damage it the same way, but then it would just get repaired. And so we would kind of have to see if this damage begins to outweigh that bone remodeling process. So I guess in summary, it certainly needs to be considered, but I don't think it would necessarily affect the damaging process, just that repair process as we go back.
Other questions, Jackie?
Thanks, Jonah. You showed a really nice agreement between the fracture location and patterns in the FE model compared to your in vitro testing on bone. And I'm curious. I don't know how do those patterns or data translate to some of the like stress fractures we see in humans. Are they similar locations?
It's a good question. They're probably not actually in similar locations. But the reason why this is actually interesting is because we're using a strain-based damage model. And so if this is an accurate damage model, we would hope that what we see experimentally will match what we see in those FE predictions. And really what would happen if we went to human bone, and if we assume the process is relatively the same, what we would need to do is just change those loading and boundary conditions. So we would model differently how the bone's being loaded. We would maybe model the muscle forces on the bone. And in that case, we would kind of hope that would cause a different type of strain distribution in human bone, but we would then see those fracture patterns in the locations that we would expect for stress fracture in human, because the only difference will be those loading and boundary conditions. But it's still, we think, because we've seen here, don't know if this is for sure the case, but we think that maybe damage is really a strain-based phenomenon. And so when we go back, hopefully those loading and boundary conditions really cause that strain, and then we see those fracture patterns where we should expect in human.
Happiness?
Very simple question. Would you define damage?
Mm-hmm.
In your model, which is very nice explanation. You talked about damage and 100%, but that's area. If you find damage and you look at the area, but what is damage?
Yeah, it's a good question. So damage, if we go to like the most fundamental definition, is really what I was talking about in those earlier slides. So it's really just this accumulation or kind of flaws in the material. So we're getting these cracks and voids. And when we try to create a damage model, we would kind of simplify this down to a representative volume element. And in this representative volume element, we would go ahead and look, because what's physically happening is the bonds are breaking between the atoms in the bone, right? And that's what's causing these cracks and voids. We can't exactly model that. So we use this, this damage fraction, which we kind of hope that when we look at this total area, we're getting a relative estimate of basically the significance of those fractured bonds, because we're really just forming a crack or a void. And so that's kind of the base definition of damage, is that really the fraction of the damaged area to the total area. But then, of course, when we go to the continuum level, we have to kind of calculate damage in a different way, because we can't do that histological approach where we're actually counting up these cracks and voids, especially when they're at that micro scale. We can't really image them. We can't do histology. And so we use a continuum mechanics approach that kind of works to, I guess, estimate how much damage or how many cracks and voids are being produced throughout those loading cycles. So here we use a strain-based continuum damage model, but there are plenty of damage models that try to estimate that based on many, many different factors. So it becomes a pretty complicated phenomenon, but at the very, very base level, we're really just looking at this total area of the cracks and voids in comparison to the area that we're looking at.
It's basically cracks and voids in the bone.
Yeah.
Could it be just something not very visible, like?
Yeah, it can be very, very small. Like usually this is on the micro scale. So these cracks are not visible to the naked eye, but we do still account for those in these continuum models. Yeah.
Just to kind of follow up with what you were talking about with the volume element. So I might have missed it when you were describing it. Is it a composite material? Do you have like fibers embedded within a base material? Like what are you assigning your modulus to?
We don't. We assign it to the individual elements. So we're not using a composite material, but we do have heterogeneous properties across the whole model. So we're really assigning an individual elastic modulus to each element in the model, but it's not like a composite material. Each one of those representative elements wouldn't have like different material properties across them. It would have one elastic modulus in each one of those elements.
Okay. And then you also mentioned the boundary conditions. So how are you describing your boundary conditions, and how do those relate to like in vivo?
Yeah, that's a really good question. So when we develop a model of this sort, what we really want is to simplify those loading and boundary conditions as much as we can. So we don't want our loading and boundary conditions to actually influence our results. We want to have as much confidence in those as we can. And so what we do here is just simple uniaxial loading. And we have a fixed support at the distal end of the bone. And then the proximal end can only translate in the Z direction. And so we simplify this out as much as possible so that when we see this damage accumulating, when we try to measure those strains in the bone, we hope that it's only due to the change in the material properties and not because we've incorrectly modeled our loading and boundary conditions. Now, when we translate that to human bone, of course, this is way too simplified to do in human bone. But again, similar to your question, is like when we go up to human bone, really all we have to do is change the loading and boundary conditions to match what we expect to see in vivo for a human. And so we would maybe model those muscle forces, we'd model those boundary conditions, and then we should still see that same damage, hopefully, incurring in the same way, but it would just be in different locations, maybe at a different rate, only due to the change in the loading and boundary conditions. So as we develop it, it should be very simplified, but then once you have the damage model, you should have infinite freedom to change those loading and boundary conditions and see how it performs.
So if you're optimizing based on getting those same outcomes, but you have multiple free parameters, and then you have additional assumptions and simplifications, like not incorporating like composite fibers or things like that, do you think that the optimizing model actually, like, that's a good, there's any limitations to doing that essentially?
Yeah,
like, are you converging on the wrong things?
No, definitely. Yeah, we certainly could be. It's not really easy to know if we are or not. And again, you can make this as infinitely complex as you want. The biggest challenge, as we kind of talked about, is in that time that it takes to optimize. So we're looking at 1 to 2 months, and in literally like the most simplified way we could model this. So if we start to model like composite materials, these fibers, if we start to go any more complicated, we'll then start compounding that computation time. And so this is sort of a proof of concept, and there's certainly plenty of limitation to it, but it does show that hopefully if we want to go that route, we can then make it more complex. It's just increasing our waiting time to optimize that model.
So I have a question about the cross section of the bone that you were showing at the beginning of your presentation. The propagation of the cracks are in some like plane.
Yep.
In that cross section. So have you taken into account the fact that the bone is the symmetry of the bone? So my main question is that this propagation is different in different directions.
Mm-hmm.
So for example, in that plane that you were showing us, maybe some crack is not propagating as intense as other like cracks.
Yeah.
So have you taken that into account?
Mm-hmm. That's actually a really good question. So we do model this as an isotropic material, at least on the individual element level. So the short answer is no, we don't take that into account. Again, this kind of goes back to this computational time problem. Is every time we make this model more complicated, more complex, yes, we're more accurately modeling the true behavior of bone, but then the big trade-off is how long it takes to optimize. So the short answer, no, we don't. We do model this isotropically, but it is actually a direction we're considering going in the future as well.
Do you have plans to like introduce resting periods in your fatigue loading protocol to see what happens to the bone?
Mm-hmm. Yeah, it's another good question. Do you mean like if we were modeling this on human bone?
No. I mean like
interrupted loading?
Bone resting periods, not continuously ongoingly loading it. Like, because realistically speaking, like rabbit bone is not under ongoing cyclic loading.
Mm-hmm.
So
I guess so. I just want to make sure that I know what you're getting at. So if we were to do, there's two different things that I think you might be touching on. So one would be if we're doing just straight interrupted loading. So we load this bone, we allow time for those residual strains to kind of alleviate, and then we wait, and then we reload the bone and do that, so on and so forth. So if we're talking about just straight interrupted loading, no, we don't do that here. And this model actually wouldn't account for it because we wouldn't actually address those residual strains after we wait a particular period of time. But if you're more getting at the remodeling aspects of, well, loading your bones, like if we were doing this in vivo with a rabbit, which again, this is actually a direction we're going to as well, then yeah, exactly. So we would model that. We would then load the bone, we would see the damage, we would allow, excuse me, we would allow the rabbit some time to heal and remodel, and then we would go and load again. So that is a direction we're going on the remodeling side. Yeah, thank you for the question. It's good.
Other questions? Yeah.
Jonah, do you think the density and modulus relationship is the same for a damaged versus an undamaged bone of equal density?
Good question. What I would expect is on the individual element level, we would hope that that modulus is still the same. So if we have an undamaged element, we would hope that the density modulus relationship, so say we induce some damage on the bone, and then we went back and redid this density modulus relationship. I actually don't know that it would capture the effects of damage. You probably would get a slightly different relationship, but I think what would truly happen is that on the individual element level, just because damage has occurred somewhere else in the model, it shouldn't affect the true material property of an underlying element somewhere completely unrelated. But the model as a whole, yeah, would affect its stiffness. So you probably would see differences in the density modulus relationship. I'm actually not sure, but that's an interesting question, something to probably look at.
Yeah, it only seems to make sense when I think about like a really ridiculous scenario where
Yeah.
they're completely separated or something, they're rubbing against each other. But in
Yeah.
a small amount of damage, I agree with you that maybe it doesn't make a difference.
Yeah,
It's just cracked.
it would actually be interesting to test that, like take one of these bones that we've optimized on, damage it, and then see if we do get the same relationship. There's actually a relatively good amount or relatively good number of sources of error in that optimization process. So I actually have no clue how it would account for that, but it would be cool to see.
Can I, devil's advocate? I mean, I've thought about that, so I don't, but when we do a material test and we cyclically load it, no matter how much damage is incurred, the apparent density stays the exact same. Material's not going.
Yeah.
Roughly the volume's not changing, right? So, but the stiffness is degrading. And so that right there tells me that you would have to have a
Same.
different relationship between density and elasticity.
Yeah.
If you have damaged material versus having undamaged material.
But isn't that what your model is all about?
That's what our model is for.
I mean, your model says that you have this density damage relationship, and actually the question that I have is, if I understood it correctly, you assume it's linear and proportional. Is that based on measurement? Is that based on intuition? Is that based on previous work?
Between the density and the elastic modulus.
Yes.
That's based on previous work. So that was all those density modulus relationships that have been developed in the past. Yeah, I think it is a relatively valid assumption, is really what's kind of the gold standard right now.
What I was curious about is that the geometry of the damage doesn't seem to matter. And I was just imagining I have one crack, you know, in your long bone, and the crack is exactly aligned the long axis, or it's exactly up, or it's diagonal. I would assume intuitively that has a very different effect. But the geometry of the damage doesn't seem to be accounted for in your model.
So, okay, you are right. It will have a different effect. So we'll see different changes in the stiffness, and kind of similar to the question there in the back. We'll see changes in stiffness behavior of the whole model, depending on the orientation of, let's say, like, we go back just a couple slides. So if this crack is oriented in a different direction, the total stiffness of the model will behave differently. Now, on the individual element level, we wouldn't model the direction or kind of the shape or orientation of that crack or that void. But what we do see across a number of elements is, yeah, we're actually getting like an interesting fracture pattern. And we hope that that fracture pattern is kind of due to strain, because we use a strain-based damage model. And so if it was truly the case that we were getting, I guess, like a linear strain pattern here going down the axis of the bone, the model should account for that, and you'd see like a big fracture going down that long axis of the bone. But on the individual element level, we don't model that. We just hope that it shows up in the end, which it kind of does seem like it does when we get to kind of that macro scale crack.
So to follow up my previous question, that you were using the isotropic material for modeling, for the mathematical simulation, how did you validate your experimental data against those like mathematical simulation? Because as you said, those were not like realistic, but your experimental data, they are realistic.
Yep. No, it's a really good question. So part of what we're doing, so we're only loading uniaxially. And what we would see a huge effect from with the isotropic or anisotropic material properties of bone is when we load in torsion. And so I do expect that if we actually were to apply torsional loads to this model, we would underpredict strain in that direction, in the torsional direction, because we model this isotropically. But you're right, like that introduces some level of error. It's not necessarily completely valid. But because we're loading uniaxially, there's actually a very limited effects from the anisotropy of bone when we're loading in that one direction.
So because one of the graphs that you were comparing these two data together, I remember that there was no significant difference between those like models. That's why I asked this question, because again, you're using a mathematical model that is not based on the bone itself, but your the comparison between like these two data, they were like literally the same.
Yeah.
So that's why I asked this question.
No, it is a good question. And I think I would expect, I don't know this for sure, but I think that's exactly why, because we're loading just uniaxially. And I bet if we were to do this in torsion as well, and we didn't change the model and we kept it isotropic, we would not see correlation like that. So you're totally right. But that is also like a next step here too. We do want to approach as accurate of a model as we can to true bone. Again, we're still limited by the computational time in these models. So this is some preliminary work, and we're just trying to sort of tease out this entire process and kind of give a good proof of concept. But all these things that we've been discussing, they're really directions that we need to go to improve this and make it more realistic.
And this computational model that you're thinking about, did you write the code yourself?
Yeah.
So are you, because I'm not super expert in this area, like coding and stuff, but is it efficient enough? Like, because there should be some like efficiency like consideration when you're like writing these codes. And again, I'm not super expert, but if you like reevaluate, it can be like more efficient and take like less time.
Yes.
This is a suggestion, just.
No, it's actually, it's good suggestion. I'm also not an expert in the programming side of this, but one thing I will say to kind of give you a frame of reference. So the script itself that's running, it takes maybe 10 seconds.
Yeah.
10 seconds max. But every time that script runs, we're doing an FE simulation. Now that takes a lot of time. And so the kind of bottleneck is not the code. Like we could look at small efficiency increases, but it'd be on a scale that really wouldn't impact this optimization at all. The big issue is in the finite element analysis and the pre-processing of the input files, and these things that we can't really get around because we're using an FE software. And so I don't really have any control over that aspect of it, but the code itself is pretty much, I mean, it's pretty bare bones. It's
Again,
about,
that's why I mentioned that if you were to write the package for the finite element code that that could meet that code that you were already written in the the Python, so you can increase the efficiency of your total coding and programming.
Yeah, and you're hitting on all the future directions. We're actually looking at doing a UMAC here, which should allow us to bypass at least the pre-processing time. But yeah, I mean, we can go all the way down to doing the finite element analysis ourselves and trying kind of bypass some of those steps that go through in the software and hopefully make this quicker. But yeah, then we're just kind of balancing out where we want to spend our time on. We want to improve the model itself. We want to decrease the computational time, probably both eventually. But yeah, I mean, it's a lot of work to do that, so we have to figure out where we want to spend that time.
Not the most time efficient in the short term.
Yeah.
Brent?
Can you just clarify how long it takes to run one simulation to failure? Yeah, the optimization takes months. That's to get the constants. Now you have the constants. How long does it take to put in a new model and figure out when it's going to fail?
Yeah, another good point. It really does depend on the fatigue life of that phone. So if it has a higher fatigue life, or if we're loading more high cycle fatigue, it's going to take much longer. But if we're looking at let's say 12,000 loading cycles for the fatigue life, this would probably take about 2 hours to run.
Well, a couple of questions about the optimization, just because it takes months. First one, on the material properties, were they 5, 6 locations you used? Do you equally weight those?
They are equally weighted, yeah.
Would there be some benefit to, because if I just look at this here, I would kind of get the sense that if you're a little bit wrong, and I think it was E5 or E6 that was at the top here, if your modulus was out by a little bit there, you probably have a lot of error. But if your modulus is out down the distal end of the tibia there, you're probably fine.
Yeah.
So is there some benefit to that?
It's a good point. I don't know though. I wouldn't know how to weight them then though, because I don't have an idea of whether or not that material is actually off. So I don't think I'd be able to determine weightings.
Just can potentially optimize it at the same time.
Yeah.
The second one on I think your first one's convex, but your second optimization loop, is that guaranteed to be convex, or is there a chance that you're at just a local optima here?
Actually, in both cases, we are probably at a local minimum.
Sorry.
No, global all around. No, in the material model, so I didn't talk about the femur, but one interesting thing that we saw in the femur is this optimization was super short in comparison to the other groups. And I think for exactly that reason, as we sort of started with these initial conditions, right on some gradient, and it just approached that gradient super quick and minimized there. So we didn't get great results. I mean, you saw the femur was much worse in its predictions. It was a 0.73, I think, correlation. And I think that's exactly the reasons we're converging to these local minima. And it's really a challenge that we face in both of these models in all optimization. Again, as this is preliminary work, what we will be doing is just testing different initial conditions, growing the simplex, trying to capture as much of the solution space as we can. But yeah, that's kind of the next direction, is to sort of see if we are converging to some local, or we're kind of getting hopefully that global within space of the expected density for both.
Just to kind of add on that, in terms of using the Nelder mead, what criteria did you use to determine that that was the most appropriate algorithm?
I could, in this case, use pretty much any gradient descent based optimization technique. We used the Nelder mead method for a couple reasons. It's very efficient, and it's also kind of, maybe show. elements here. So it's a again, a gradient descent-based optimization method, and we have this initial simplex. And the good thing about having this initial simplex and kind of crawls towards that final solution is that it can converge to a non-stationary point. So we kind of talked about these nonlinear effects of damage, and even when we do the material model optimization, like you can change that material model, but every single element is dependent on that material model. So you get like a crazy redistribution of stress and strain for just a small change in that material model. So you kind of have this non-stationary minimum that we're trying to approach. And so that's kind of the big advantage. And then the other one, because we can control that simplex, hopefully we can do exactly what we're talking about here, is really grow it and try to search for different solutions within the space and kind of move that initial simplex around and crawl towards those.
Other question? Yeah.
Yeah, just about your processing time. Thanks again, Jonah. But do you have to do this in-house or can you guys use the high performance computing cluster?
So we do this in-house. Now, here's the weird thing about this whole optimization. So this is actually like when we do damage model optimization, we run all those simulations in parallel. So this is all parallel processing. We actually wouldn't benefit from using any type of supercomputer here because our bottleneck, again, and this is why it might make sense to go back and kind of develop our own FE method to do this, or do a UMAT to actually cut down on this pre-processing time, because the bottleneck is actually the time that the software that we interface with takes just to analyze the input file. So just kind of reading it into memory, doing all of its data checks on that. And if I could cut that time out, this would be like twice or 3 times as efficient. And so doing it on a supercomputer, it wouldn't affect that input file processing time. What it would affect was it would we get those finite element results quicker, and we could probably run the script a little bit quicker. But again, that script only takes about 10 seconds to run. It's that initial input file processing. It's super frustrating that that takes like 5 to 7 minutes. There's nothing that I know of to bypass that other than doing a UMax, developing our own FE method. But once that's bypassed, it actually goes quite quickly. Like we can do the simulation in like 1 to 2 minutes. And so it's really just that processing time. So even when we run the simulations in parallel, we don't even see a noticeable, or yeah, on parallel processors, we don't see a noticeable effect because they're still that quick already. Kind of the unfortunate case, but yeah, big challenge that we need to address.
Very nice presentation, Jonah. Thank you. I might have missed this from your presentation, but in your cumulative damages slide, I wanted to know if you have defined any particular failure criteria for your FE model particularly. Is there some kind of erosion defined or something like that? Or how do you define the failure state for the model?
Yeah, so that's kind of the failure criteria determination part. So in each one of those elements, they reach that critical damage threshold, they're removed. So those elements have failed. And then when we go to this whole model level to say, when has this actually reached fatigue failure, we're looking at stiffness degradation. So we use this 25% stiffness degradation. So every cycle, we measure how much displacement the model undergoes. And once we've lost that 25% stiffness, that's when we define it. Have fatigue failed.
Any other last questions? Yeah, Walter.
Yeah, when you did the verification there with measuring the strains, and then you got this R-squared of 0.97. Did you try to use some of the strains for optimization and then predict the strains for points where you measured the strain, but you actually didn't use as input into the minimization, the optimization?
That's a good question. That's exactly what we're doing right now. We're not doing it on the same bone, but we'll optimize this model on bones that we've just looked at right now. And then we're doing validation with a different set of bones that it hasn't been optimized for us. So we'll see what those predictions are like. So yeah, the data we saw, that was from the same bones that it was optimized on. And we're just about to validate this in a completely different set where it's not optimized.
For the same points, but on a different bone.
But we should be able to do any points.
That's what I was wondering, you know, if you just take an arbitrary point, and put a couple of strain gauges on there, which would be quick to do, and then not use those as input, but then for the optimization, but then see, does it predict at some other random places strains as well?
You actually, that's a good idea. Because one thing that we would benefit from doing that is we would actually have to load fewer bones if we do it that way. So we could load the same bone, read off the strain outputs, take half of them, use that for the model, and then check it on the other half. So it's a good idea. But I do think it would be more interesting to validate it on a different set of bones too, because then we also can see how it behaves on like a completely different animal, completely different limb. Because I think somebody might argue then, well, you've optimized it for the material of that particular bone, so you'll probably have better predictions in that same bone. And then if we go to something completely different, I think then you can't really argue that. So both are actually.
I was more thinking about the argument that if you measure it at different places that were not used and the predictions are very wrong, then you probably need to do something. You know?
Yeah, exactly. That's a good point.
In your equation there, you know, the modulus fracture damage equation, does A and B have any meaning, or are those completely arbitrary values that just come out, but they don't have a structural or any other meaning that you can identify?
As far as I know, there's not really any structural meaning behind them, only actual like parameters that we have of meaning. In the damage model, it's that one VC strain, time step parameter, and then that A and B is just kind of like scaling factors to sort of change the shape, like how quickly that damage accumulates. And then in the material model, kind of the same thing. So the A and B, as far as I know, don't really have any significance. It's just how we get that optimal relationship, kind of that exponential relationship between density and elastic modulus.
And just coming back to the global or local minimum that you might be finding, what kind of an optimization is this? Are you doing convex programming, or is this simplex? Is that actually a linear program, a linear optimization, or what kind of boundary conditions do you have for your, if any, do you have any boundary conditions in optimization?
We do. So I try to use, and we're going to play around with boundary conditions for the optimization itself. The way that I've kind of conceptualized this right now, I have it as broad as possible to try to search as much of the solution space as we can. So when we change that location to simplex, we can then move around. But yeah, what we would do kind of ideally is we know the approximate densities that we should expect for bone. We know the approximate elastic moduli that we should expect for bone. And so we can bound the optimization on those two axes. So you might have like an elastic modulus between 0 and 20 gigs, and then a density between 0 and like 3 grams per centimeter cubed. And then that's how we would bound the optimization. So we wouldn't let the final output go past 3 grams per centimeter cubed in density and 20 gigs in elastic modulus.
But I mean, more conceptually, the optimization programming that you do, is it linear, is it a quadratic, is it a convex programming? Because if it's convex, then you can calculate the Hessian matrix, and you could see whether or not have a convex programming system. And if you do, then you would actually know whether or not you reached a global or a local minimum.
That's a good point. I'll be honest, I actually don't know. Here's what I'll tell you. As much as I know about the optimization, we're using a gradient descent based optimization. I don't know if it's convex, quadratic, linear. I actually don't know the answer to that.
Okay.
But that's certainly something I guess I'll have to look into. Because if you can, so you say that you'd be able to find the global minimum?
Well, if you have a convex programming system, then you can mathematically show that your minimum that you're finding is actually unique, and therefore your local is also a global minimum.
Okay.
And if it's not convex or a linear system, then you wouldn't know that. Then you would have to test, with different initial start out with different initial conditions, and then let it go and see if it goes to the same place to kind of get at least a feeling whether or not you're going to the right place.
Right, so
but if you look at your cost function, your constraint functions, then you can see what kind of problem it is.
It's a linear cost function.
If it's a linear cost function, then, and your boundaries are linear as well, so it's a
Yes.
linear programming system. But in a linear programming system, you'll always end up in a corner of the solution space, and that will be unique. So therefore, if it's done properly, then you should actually reach the same solution independent where you start from.
Can
I
I
will
just-
say, yeah, go ahead.
I don't know about the continuum damage model
Yeah.
and the optimization there. I'm sure we're probably at a local minimum. But I've got quite a bit of confidence in this, the density elasticity modulus results. And so do A and B mean anything? A doesn't really mean much, but B actually means something. When it comes to cortical bone, the stiffness of cortical bone is roughly linear with respect to density. When you get to trabecular bone, it's roughly quadratic. When you get to, it's roughly quadratic with density. It has to do with something called cellular solid theory, how trabecular bone fails by buckling. And buckling stiffness is, there's a power in there to some, okay? And so we get, when you do the optimization, you get some B value. That's, I don't know, somewhere between 1 and 2.
Yeah.
1 and 3. 1 and 3, okay. So I would be very skeptical of an optimization that's locally converging on powers of B that are 1.2, 1.5, 1.8, 2.5, right? I would think that you could get weird power values of like 5, 6, 7, and then it would drastically change A, or sort of vice versa. But I would be really surprised if you have several local minima where you've got that power law of B. And I could be wrong because you only have a couple samples. So maybe, but at least when you scale up, I think looking at that slope B provides you with a little bit of confidence in whether or not you are at a global or local, because there's mechanistic reasoning behind what that value should be.
So.
But you could just, I mean, that's a quick optimization. You could just redo it multiple times, keep the same gradient-based optimization and change your initial guess.
Yeah, which is what we'll do. And I do know, like, I've done this twice. We do converge to a different solution. So.
Well, that would, because in a simplex linear algorithm, you shouldn't, except if you might have boundary constraints somehow that are nonlinear.
So Folk theorem in optimization is if you get rid of the boundary constraints, like unbounded optimization, unconstrained optimization is a lot easier problem than constrained optimization. So if it's as simple as something being greater than 0, throw it in the box.
Yeah, something we'll definitely have to look into a lot more and play around for sure.
Well, we're getting good value then. We're getting something that seems to go along with experimental values that you measure directly, and then you seem to be getting values that seem biologically feasible. So, so I think you're in good thing. I'll ask you a question there. In the introduction, you talked about stress fractures, and so then you said, then you say, well, you get the stress fractures, and so, but actually injuries can be completely predicted. What's your sentence?
I didn't say it could be predicted. I said if we can predict them, then.
That's what I understood. I wrote it down. Injuries can be completely predicted.
No, it can't be, but if we
Cannot be.
can,
Okay.
if we can, then we can prevent them. That's the idea.
You believe that? So if
Do I believe that we
if
can
you see
predict?
somebody that has your 30% damage there, that then the models will reduce by 30%, and then you think you could prevent that. You could tell that person to do something that she would not get a stress fracture.
Okay, here's what I think. If we go and we say maybe we do this in like at-risk populations. So maybe it's postmenopausal women, maybe it's military recruits or female runners. Then we could go ahead, maybe do an opportunistic CT scan, run this model and see, in this case, the force would have to be much more complex, accounting for the modeling process, the muscle forces, all of that, much more complicated than what we have here. Then I would hope we would get at least an idea of the fatigue life of that bone under the loading conditions is safe for a female runner while they're running. And so we would say, once we get that idea, maybe it's such a low fatigue life that we say your bone quality is not great enough, so you need to rest and allow some more time to heal. That's where I think it could go. But there's a lot to do.
So a clinical opportunistic CT has the resolution that's sufficient for you to do this?
Yes.
Okay.
Yes, that's micro CT is certainly a lot better, but yeah, that's why like all these scans here are clinical CT scans.
Okay.
Yeah.
Last question from Brad.
I get the last question. We can predict osteoporotic fractures without simulating any kind of boundary conditions, right? We don't know that somebody's walking their dog and the leash wraps around another dog or something. We don't know if somebody's standing on the bus and the bus moves really quickly. We don't know how they fall to the hip or this and that. Well, you do a finite element model, computed tomography based finite element model of somebody, and you just simulate falling or whatever, and you can get a pretty good idea of who's at a high risk of fracture. It's not perfect, right? But in the field of osteoporosis, nobody simulates the event. And for some reason, when it comes to stress fractures, everyone's expecting us to simulate this event. What about just getting a CT scan of a runner, applying an axial load to the bone, calculating a strain distribution, and use that to determine if somebody's going to be at higher risk of fracture than somebody else?
Yeah, I mean, sure. I do think, though, it would be important to kind of, I don't know that the uniaxial loading would be great. Yeah, you'd get a strain distribution and maybe based on the bone quality or whatever, you can get an idea of whether they may or may not be at risk of stress fracture. But I think it would probably be more reasonable to try to match some type of loading condition, like for a female runner, the running loading conditions, because you get a different strain distribution. Maybe it's that their bone quality is poor in one particular region, and there we see a high stress or high strain concentration from those from the loading associated with maybe running. And then we could predict from that, because I think if we just do uniaxial loading, yeah, you get this strain distribution, but maybe in the area where we expect to see stress fracture, you're not seeing that from the uniaxial loads, so maybe you underpredict it. I don't know, but yeah, I mean, probably it would be a more realistic approach.
Because in runners, stress fractures don't occur there in the tibia, do they?
No, and this is actually, I think, part of why we see this fracture where we do. I actually think it's because of the experimental setup. So I think it's kind of due because we have bone cement there. Yeah, that's how I would kind of explain that. And certainly in a runner, it wouldn't. We'd see it in a much different location because of osteoporosis.
Awesome. Well, thanks, Jonah.